Hello, everyone. Today we are going to talk about approximate integration. As you probably remember, last lecture I was talking about some integrals which are non-elementary functions. Looking like this. For example, need to integrate something like this, and though the integral looks simple, there is actually no formula or no antiderivative for this integral. Or it can be something like this, for example, e to the power of x squared dx, no formula. So I'm going to label them non-elementary functions. Or maybe somebody was observing a signal on oscilloscope and he observed that the signal looks like this. And he really wants to find the area under this curve between points A and B, but he does not know what function is this. He doesn't have a formula for the function. So sometimes we'll need to find out the area under the curve, and we either don't have antiderivative, or antiderivative, let's say non-elementary function, or we even don't know the function. I'm going to label these two integrals with limits to show that we are searching for the area under these curves. So how should we kind of find this area if we have either non-elementary functions or we even don't know the function? Well, we are going to go back to definition of definite integral. What is definition? Definition of definite integral according to the Riemann sum. Remember that definite integral from point A to point B of a continuous function is going to be equal to a limit over Riemann sum. Limit as n approaches infinity was chapter 4 in our 5A class. Sigma from n from ni, or let's say, from I equals 0 to n f of xi with a little star multiplied by delta xi with a little star. So remember that actually definite integral was defined as a limit of Riemann sum. So you take a function f of x, divide, let me just maybe kind of review this definition a little bit because I'm not sure that everyone remembers it. Imagine that you have a function f of x over here, and you want to find the area under this function between these points A and B. How you can estimate it using Riemann sums. We're going to divide our interval from A to B into subintervals. Well, they're not necessarily must be a same length subintervals. And kind of the ends of subintervals are labeled with points xi, right? And delta xi is going to be the length of one subinterval, delta xi. And again, star over here shows that they're not supposed to be equal subintervals, though they can be, but not necessary. They're just supposed to be small subintervals, let's say. The xi is going to be any point on this subinterval. For example, you choose a point over here, and that's why we do have a star. And at this point, we are going to draw a little rectangle with a base on this subinterval and the height, which is going to be equal to the value of a function. This is going to be f of xi with a star. And basically, guys, the product over here is estimating area or elementary area of this rectangle. Rectangle with, I'm going to draw the picture. So the width of this rectangle is delta xi with a star. That's how big is this? And the height of this rectangle is going to be f of xi with a star. And we're just finding the area of the rectangle with one side equals delta xi and the height, which is going to be equal to f of xi. And then we sum up all those rectangles from A to B and kind of try to increase number of divisions. So for example, we start with n equals 5 and then steadily go to infinity or increase it to infinity. Eventually, if the function is continuous or piecewise continuous, the limit is going to become number, and this number is going to be actually called definite integral, right? How this formula is going to help us? Well, the point over here, this xi, well, can be any point on this little subinterval. So, for example, we can use a left point of subinterval, for example, a right point of subinterval, or midpoint of subinterval, just to be kind of more definite. And that's how we estimate actually the area under the curve using this formula. The only difference is going to be that, well, manually, we cannot make a limit of n going to infinity just because, like, if we do it numerically, we're supposed to limit ourselves with certain number of steps. But we can make it large, relatively large, depending on like how big is our computer, right? So let me consider an example of like how these sums are built and how people are using these sums to calculate areas under the curves. I'm going to start with a very, very super simple example, and I'm going to build 4 different sums using actually this like Riemann sum. Scroll it up and I'm going to use red color. So my example 1, my color did not change to be red. Yes, I'm going to consider f of x, a very, very simple function, which is a square root of x. Square root of x is a simple function, and it does not actually fit either of 2 reasons to estimate it numerically, because it has antiderivative, which you can use to find actually precisely definite integral of square root of x. Also, like the function is known, so we are using this function only to kind of show how the method works. Normally, of course, no one is calculating a square root of x using numerical integration. Okay, so I'm going to do the graph of this square root of x, and I'm going to set up a problem. What kind of problem we want to solve? So let's say it's going to be 1, 2, 3, 4, 5. And let's say it's going to be 1 over here, 2 over here, and y over here, and x over here. So guys, I'm using different units on x and y axis. That's why we always need to show 1 unit on each axis. So my graph, I'm going to use a different color, and my graph is going to start at 0, right? A square root of 1 is 1, approximately, of course. A square root of 4 is 2. And I'm going to just connect these points and kind of continue. So what kind of integral I want to estimate using my numerical integration? I'm going to estimate integral from 0 to 4 of a square root of x dx. Before I start working with numerical estimation, I really want to find out what is supposed to be actually the answer in this case. So let's integrate actually the function itself. So what is going to be the answer in this case? Remember that square root of x is actually 1 over 2, right? X to the power of 1 over 2 dx and definite integral from 0 to 4. So 1 over 2 is going to give us 1 over 2 plus 1, right? And in denominator, 1 over 2 plus 1 is going to give me 3 over 2. And we'll need to plug in limits 0 and 4. Well, let's do this. So 3 over 2 means that it's going to be a square root of x cubed, right? Divided over 2, divided over 3. I'm going to flip over the fraction in denominator. So divided over 3 multiplied by 2, and substitution of 0 and 4. I'm going to plug in 4 first. So I'm going to have 2, and then a square root of 4 cubed divided over 3. And if I plug in 0, I'm just going to get 0. So basically, guys, the square root of 4 is 2, and 2 cubed is 8, multiplied by 2 is 16. So I have 16 over 3. 16 over 3, if you divide it in your calculator, you are going to find out that that's 5, 3, 3, and 3, and more trees in period. And I'm going to approximate it with 5, 3, 3, 3, 3. I'm going to keep 4 digits. Wow, why? Because I actually know how many digits to keep for right now. And eventually I'm going to teach you how to define how many digits to keep. But for now, I'm just going to keep 4 digits. But we always know that it's actually more. So approximation, my actual value is supposed to be 5.333. Okay. Now, let's draw which area we are planning to calculate. We are planning to calculate area under the curve from 0 to 4. So this is my 4, this is my 0. My plan is to calculate this area, right? What I'm going to do, guys? Well, as I said, I cannot manually bring n to infinity, so I'm going to consider a certain n. So my certain n is going to be equal 4. Why 4? Well, because if I want to find delta x, which is also going to be known as a step h, when your delta x is a similar size, usually we label it as a step h, it's going to be b minus a divided over number of steps. We take the whole interval and divide on how many steps we want. In this case, guys, we are going to make every step equal to each other. Normally, the Riemann sum doesn't need this, but because we are not like computers, or let's say God Almighty, we are going to use a certain step, and that step is going to be the same for all, like whole interval. My b is 4, my a is 0, and I divide over 4, and I'm going to get 1. Well, you probably understand why I choose n equals 4, just to make our calculations very, very simple. So my step, I'm going to label step, is equal to 1 unit, and n is number of steps. Number of steps, or you can say number of subintervals. Subintervals can be. Okay. Now, guys, what I'm going to do, I'm going to consider several variations of Riemann sum. Oh, you kind of let me write down what Riemann sum is supposed to look. Riemann sum is supposed to look like sum from I equals, I don't know, we have 4 intervals, right? Well, I'm going to start from I equals 1 to 4 to count 4 intervals, or kind of, we can start from I equals 0 to 4. And f is going to be xi delta xi, right? That's my Riemann sum. Well, in our case, this delta xi is going to be the same and equals to h. Because it's the same number, we can take it outside of the sigma, and we can write down h multiplied by sigma f xi, I from 1 to 4. Well, now, what are going to be my f? That's a kind of major thing here. Usually h always will be outside. Well, let's imagine that on each subinterval, for example, from 0 to 1 or from 1 to 2, we are going to use the right endpoint. Right endpoint is for this interval is, for example, over here. And we are going to build a rectangle using that point. For rectangle, let me use a different color. Rectangle, I need some different color. Why it doesn't give me the whole, yeah. Let's see. So rectangle over here is going to look like this. We build a rectangle. Now use a right endpoint, point 2. I'm going to build another rectangle. And at point 3. Sorry, my rectangles are not perfect, but you guys can draw better. Doesn't matter actually. So we built 4 rectangles based on the right endpoint xi. So if our interval is like this, we are using this point, right endpoint, right? Well, let's see what kind of sum is going to be. First, guys, we are going to label it with or. Or means that we are using right end of the interval. Second, we are going to put a little 4 over here. 4 means that we are using 4 steps. Well, we'll need to put length of the step, and then the sum of the values at each of these points, right? Because step is same, so kind of this side is same, and the only side which is changing is height. So we can just take the height and sum it up, right? So we are going to have f of 1 plus f of 2 plus f of 3 plus f of 4. Sorry. They are going to be f of x1, x2, x3, x4, but because they are actually like already 1, 2, 3, 4, I'm just going to kind of name them. So my step is equal to 1. F of 1 is a square root of 1. We are not using the actual integral. We are using the function from under the integral. This is my f. Okay. Square root of 2, square root of 3, and the square root of 4. So we are just going to add up all these square roots and multiply by 1. Well, multiplication by 1 is going to do nothing. We do know that square root of 1 is equal to 1, so maybe I just going to put it 1 plus square root of 2 plus square root of 3, and the square root of 4 is equal to 2. So let's calculate it, and give me a second. I'm going to pause my video for a second and just use my calculator to calculate it. Okay, guys, I got my number and it's a 6.1463 if I round up to 4 digits. So approximately equals to 6 point. It's not very close to what I'm supposed to have, but somewhere around, right? So this is called right-hand sum estimation. Why it's estimation? Because it's not actual value, right? Actual values, some difference, has some difference. Now, guys, what is going to happen? You see that my first, before we move on, before we move on, you see that estimation is a little bit larger than actual value. Why? If you look at the picture, it's kind of obvious, right? You see all these rectangles are not only covering area under the curve, but a little bit on the top over here, a little bit on the top over here. And this on the top is actually making that extra value. Now, guys, what is going to happen if instead of the right end of the interval, I decide to use left end of the interval? Well, I'm going to have left hand sum. And L4 is going to be same H, but now on each interval, I'm supposed to choose a left side. Left side on the first interval is this, and that's going to build for me the rectangle with 0 height. Left hand over here is over here. Left hand at 2 is over here. And left hand at 3 is over here. I still have four rectangles, right? Now they're sitting below the function. Guys, I don't want to write down the general formula. I'm just going to plug in everything, right? Square root of 0 plus square root of 1 plus square root of 2 and plus square root of 3. So basically, I'm going to have 1 multiplied by 1 square root of 2 and the square root of 3, which is kind of same value as this one. The only difference is going to be that it's less by 2 units. So my value, I'm just not going to even use a calculator. I'm just going to subtract 2 because it's going to be 41463. You see that my value over here is a little bit less than 5333. Well, we kind of see it because all the rectangles are sitting below, actually, below the curve. Now, what if I choose not left point or right point, but I choose a middle point? I'll need a different color. Let's choose a middle point, middle point, middle point over here. How everything is going to change? Well, for middle point, we are going to label it as M. Still we have 4 subintervals or 4 steps. We still are going to have H. What is going to be the middle point on each of these subintervals? Well, let's kind of look at the picture. So my first middle point is going to sit over here, right? And that's going to be 0.5. My second middle point is 1.5. Third middle point is 2.5. And the fourth middle point is 3.5. Guys, I don't have much space to kind of do labeling, and I hope that you kind of understand how do we choose middle points. They're just in the middle of the interval. Okay? I'm increasing a little bit everything. So it's 1.5, not just 125. Okay? Well, I'm going to put everything under my square root again. So 0.5 plus square root of 1.5 plus square root of 2.5 2.5 and plus square root of 3.5. See, what are we going to have if we use a calculator? Well, guys, actually, I used my calculator already ahead of time, and I calculated that this sum square roots is going to be equal 5, 3, 8, 3, 8, and more digits, which are going to round up to 5.3838, or 3638. That this blue color is not my best one, right? If I compare my answer over here to what I'm supposed to have according to precise formula, I'm going to see that my answer is much closer. My precise formula is 5333, and I see that my answer here is much more close, right? So if I'm planning to do estimation, maybe I'm not going to use left-hand sum or right-hand sum. Maybe I'm going to use actually middle point. Well, let's talk about errors of estimation, because you see that why do we call it estimation? Because we are not going to get precise value. So what are errors of estimation and how do we kind of write them down, describe? So guys, we are going to use letter E for errors. E. And for example, error of estimation in a right and interval. We are going to take precise integral from 0 to 4 and subtract what we estimate. In our case, we are going to have 5.333 minus 6.1463. I'm going to calculate it. I'm going to write down all of them and then put numbers, okay? Error of estimation left hand is going to be actual integral minus left, that's 5.333 minus 4.1463. And the last one is error of the midpoint, which is going to be 5.333 minus what is my answer? 5.3838. Well, this one is easy to calculate. I think I'm just going to write it down. So the error here is minus 0.0505, right? For this two, I'll need to calculate it just a second. Yeah, guys, I calculated the errors. So for right hand estimation, we have minus 0.813. For left hand estimation, we have 1.187. And if you compare it to midpoint estimation, there is a big difference, right? Midpoint estimation is like, looks like 10 times better. Well, what does it tell to us? First, it tells us that sometimes error is going to be less than 0. Sometimes it's going to be greater than 0. Usually, guys, we are going to talk about error bond. So let's write down general formula for midpoint rule, like so, guys, general formula is going to give us approximate estimation of this number, because we kind of not sure that it's going to be greater than 0 or less than 0. We are going to estimate absolute value of this number. And we are going to say that it's going to be less or equal than k b minus a cube over 24 n squared. What is k over here, guys? K over here is going to be a number which is going to be greater than the second derivative of my function, absolute value on interval from a to b. So take your function, calculate second derivative, then take absolute value of that value, find the maximum of that absolute value, and then choose any number which is greater than that value, and that's going to produce number k. Well, let's Let's see. Why do we need this formula? We can just kind of calculate the difference, right? Yeah, guys. We can calculate the difference when we do know actually precise value, right? When we do know this value. But if you don't know this value, you cannot calculate this difference, and you cannot find out like how far your estimated value is from your actual value, because basically, guys, you don't have antiderivative, or you even don't know the function. Let's see what this formula is going to give us in our case of a square root of x. Let's see how the formula is going to work, okay? And after that, we are going to talk about some other rules. So first, guys, we do know for this formula everything. B and A are like 4 and 0, right? Number of divisions is 4. We don't know K, which is maximum of second derivative on the interval. Well, let's find it. So my function here is a square root of x, right? My first derivative is 1 over 2 square roots of x. Differentiated. It's 1/2, right? 1/2 and minus 1/2. What is my second derivative? My second derivative is going to be 1 over 2, and I'll need to differentiate this x to the power of negative 1/2. Let me write it down as a rational exponent. Otherwise, it's going to be too hard for you to imagine why derivative is this. So I differentiate actually this expression, and I'm going to have what? Negative 1 over 2 x to the power of negative 3 over 2 if I subtract 1, right? Well, if I combine everything, I'm going to get negative 1 over 4, and that's going to give us x to the power, the square root of x cubed over here, right? If I represent this power as a like in familiar rational fraction. The formula tells us that we need to take absolute value. Why? Well, because sometimes derivative is going to be negative. Actually, it's not going to affect the formula except the minus need to be dropped. So absolute value of second derivative is going to look like 1 over 4, and here square root of x cubed, right? So we need to find maximum of this function on interval from 0 to 4. What is going to be? Well, guys, this function is going to, I'm going to graph it. This function is going to look a lot like 1 over x. Just if you kind of look at this more carefully, you're going to find out that's 1 over 4. And here, if you kind of, you have you have 3 square roots here, a square root and the square root and one more square root, which is cubed, right? This one is just x. So basically, guys, it's 1 over 4. It's 1 over 4 x and square root of x. So it's going to look like 1 over x, but because you're going to divide by bigger number, it's going to look a little bit like more slim. Okay, that's going to be x and that's going to be y, your function, approximately. Well, if you look at your function, you're going to see that, unfortunately, the function does not have a maximum on interval. So maybe it's not going to be that easy to do the estimation of the error. Well, what we can do, guys, we can consider like value x equals 1 and estimate it from 1 to 4, not from 0 to 4, because you see that actually around 0, it goes to infinity. And means that the formula is not going to give us a good estimate. Uh, well, if you consider interval from 1 to 4, 1 to 4, we're going to just plug, the maximum is going to happen over here, right? And we can kind of figure out that if you plug in 1 over here, we're going to get 1 over 4. Yeah, that's not going to be precise value. It's approximation, but still going to be good. So let's do the estimation. What formula is going to give us? And that was not a very successful function to choose in terms of finding the error, estimating the error. I'm going to use a 1 over 4. My b is 4, my a is 0 cubed over here. 24, and my n is equal to 4 squared. Well, I have so many 4s over here. So I have 4 cubed. Here I have 4 in denominators and 24. and then 4 squared. Maybe this 4, and this 4 is going to cancel, and I'm going to just get 1 over 24. Well, which is approximately, let me quickly calculate it. Let's divide 1 over 24. 4. So 0.0416, which is approximately 0.041. Well, why my actually estimation for error is a little bit bigger than my actual error for midpoint rule. My error for midpoint rule is 0.5, right? And here I have 0.4. Well, because I arbitrarily choose actually end of the interval as 1 to make it simpler, but actually because my interval is to 0, that this number k must be taken bigger. But normally, guys, you are going to have nice functions without like this special point. Just like was my choice to make calculations easier, but for errors, it's not going to look better. Okay, so I think for the first part of the video, we are going to stop at this point. There are 2 more methods to do estimation. And I want to talk about these 2 more methods in the second part of the video. Otherwise, this video is going to be too long.